My name is Cullen. Today we'll be going over the results from the gas turbine jet engine experiment. So, brief little overview of the purpose of the experiment. We just wanted to gain an understanding of pretty much how this whole system works, as well as being able to understand and interpret the inputs and outputs of it all, and the power generation of this whole system. So, I know Bryce went over it, but a brief little overview again. So, compressor inlet, compressor itself, compressor outlet. This is going to be our first turbine, our second turbine, our generator. This right here is a free turbine. This is the outlet, and this is the inlet. So this is a simplified schematic of what I just showed you. So, brief look at this. You have your compressor, your combustion area, your two turbines, your generator, and your power output. This is the display screen that you're actually going to see when you run the program, not the one that the lab manual tells you. It's actually much better looking than the one the lab manual has. And when you're running this, it's kind of important to note that before the system starts to reach and starts to run, you want to press this button right here, log data, and it's going to live log the data of the experiment as you're running it. I was under the impression that it did it afterwards, so it took us a couple tries because I did not press that button, and so as a result, we had to run it 3 times in total. So definitely make sure to press that button before you run it, or else you're going to look like a huge ass for the rest of your group. This right here is the control panel. So this is the tip, the turbine inlet temperature. This is the engine RPM, the generator RPM. These are some dials that I don't exactly remember what they are. This is the master key, the go button, the stop button. And then these are your 2 primary levers that you're going to use the whole time. This right here is the throttle lever, and this, which affects the engine RPM, the turbine RPM directly. And then this here is the load lever. This is for the generator. Primarily affects how much load you're putting into the generator. And on this load lever here, I'm sure you can see it in between my 2 fingers, is a little pin system. It's a spring pin. And when you're running it, it's important to have it initially in this pin mid position. So other important operating parameters before you actually start the experiment is you want to know your fuel source. And Richard told us he basically had like a homemade backwoods 50-50 diesel kerosene split of fuel. And so we weren't exactly sure what the ratio was or even what type of fuel was. And so as a result, you want to know your fuel energy per unit volume as well as your fuel density per unit volume. But since we had some homemade thing, I didn't exactly know how to go about calculating it because I didn't think it'd be simple as, add the 2 and that's it. And then another important parameter is the barometric pressure of the ambient air around you. Ours was 30.27 inches in mercury, and we got that from just the AccuWeather app on my phone. Oh, and the reason why the barometric pressure is important is because the incoming air pressure affects how much work the compressor has to do on the air. So some operating conditions. This is the apparatus itself. This is the inlet. Over here is the outlet, and you can't see, well, you probably see a little bit. There's a canopy above us, a little tent. And so what you want to do is you want to make the outlet flush with the canopy end, because this is going to exhaust really, really, really hot air as well as just fuel, and you don't want to be anywhere near it. And when you're running this thing, so what you want to do is you want to take, like Miranda's doing here, you want to take the throttle. You want to bring it up to throttle, and you're going to run it to about 43,000 RPM. Now, when that happens, this little display board here will say the word run on it. Once it hits run, you now know that this turbine has hit essentially steady state. And once this hits steady state, you can start playing with the load lever to see how the generator is affected. That was overall how we ran this entire experiment. So here are some results. So we have the compressor inlet pressure and the outlet pressure, as well as the inlet temperature and the outlet temperature. And we ran this experiment on the try that we actually worked on for about 220 seconds. And so this is what it looks like over that time period. And here are the turbine 1 results over the same given time period. So as you can see, the turbine pressure and the compressor pressure actually have the exact same trend, but for different parts. So turbine inlet pressure, as you can see here, is the one that rises, whereas the compressor outlet pressure is the one that has that as well. And they have the inverse as well for the inlet pressures and the outlet pressure there. And then the turbine 2 pressure and turbine 2 temperature. Now, one important thing I want to talk about the turbine 2 temperature is about 45 seconds into it, we actually had, no, it's about 20 seconds into it, we actually had this one strange data point that had a negative 8,000 degrees Celsius temperature. Now, I am not sure as to why that was there.
Really cold.
Right, I don't understand that. My only possible thought was that I actually just don't understand it. It shouldn't be like that. Because when I go to the zoomed in version of this graph, that's what it looks like. And that negative 8,000 points all the way down here. So as to why that outlier exists, I'm not entirely sure. But this is what the turbine 2 temperature actually looks like with the inlet and outlets related to each other.
It was when it was starting.
Yeah, but it wasn't quick enough. It wasn't immediately. It was 20 seconds in, which I don't, like it says 0 here, but it's not.
Because it takes a while before it picks up.
Right, it does. But it's just the fact that it dropped from 300 degrees Celsius to negative 8,000 on the data sheet.
So that, for me, that is just more or less like, what would I say? Signal issues.
Just system error, something like that?
Yeah.
Okay, that makes more sense. All right, and here are the RPM results. And so Bryce had it on the last little slide of his thing, these strange little green, yellow, and blue dotted lines up to here. So what that is, it represents the excitation points of the generator. And the excitation is how much current is being produced from what I understand. And so pinned is the initial point where you're running the engine up the throttle to reach steady state. Minimum excitation is when the least amount of current is produced by the generator, and maximum excitation is where the maximum amount of current is produced by the generator. And so I located those 3 points, and I used them, they're the same time, same points in time for all of the plots you're about to see. And what that is this just shows you at this point how or where the RPMs of either the turbine or the generator is. So here's some electrical results. So the output voltage, when we hit around steady state, you can see that the voltage produced really increased, as well as the current. And you can see here this max excitation. This is hand drawn, this line, so it's not going to be perfectly vertical. But as you can see here, the max excitation is near where the current reaches a peak. In terms of power produced, it followed the same trend as the current and the voltage, which makes sense because power equals voltage times current. And the fuel flow here was fairly steady once we reached steady state and brought the system up to full throttle. So my first analysis point that we looked at was when the engine RPM peaked. And so to do that, you just control F your spreadsheet for the engine RPM. And this is kind of confusing the way to read it because it's not perfectly labeled. But this is the compressor inlet temperature, compressor outlet temperature, turbine 1 inlet temperature, turbine 1 outlet temperature, which also acts as the turbine 2 inlet temperature. And then this is the exhaust temperature, or turbine 2. And then pressures correlate the exact same way as the temperatures. And then here we have N1, which is my turbine RPM, and we have N2, which is my generator RPM. And as you can see, the max RPM that we reached for the turbine was about 45,000. So performing an analysis using the steam tables, we determined the specific enthalpies at each one of these points. And then using that, we were able to determine these parameters, so specific work of the compressor, the specific energy about the fuel, specific work of the turbine, the work of the power turbine cycle, the efficiency, and the specific work of the free turbine. It's noted that we got a thermal efficiency of 28.3%, which is pretty good. It's about what you want, and it's about what we'd expect. I think the expected calculation came out to be about 26%, so this is actually a little bit higher. Engine performance analysis, a little disclaimer before we start this. The last number you see here says we have a Mach number of 1.23, which believes that we broke the sound barrier. I don't think that's correct. I don't think that's accurate, and I think the primary mistake that I made that on the air velocity, which I had 420 meters per second. That is the air velocity coming into the compressor at the inlet area, which I do not think is accurate, so I do think I made a mistake somewhere in the calculations, but I'm not exactly entirely sure as to where. I also received an air density significantly lower than the typical air density. Typical air density at sea level is 1.255 kilograms per meter cubed, and I had about, 10% of that, so I think that's also an issue with my calculations. But like I said, I calculated the air density using this equation here, and using the compressor inlet pressure and the compressor inlet temperature, as well as the universal gas constant, which I did make sure I switched out of from moles to kilograms to receive this air density there. And then I used a Bernoulli's relationship to reach this air velocity right here. And then I used this with an assumed inlet diameter of about 4 inches. And I then used that same result from Q to calculate the mass flow rate. So I'm not exactly sure where I messed up, but I'm confident based on this Mach number that that is not correct. Because while we did have to wear head ear protection, no sound barrier was broken while performing this experiment. Promise. So we also wanted to determine how well it performed electrically. So we wanted to pick 3 analysis points to determine the electric performance of the entire system. That is where the lever arm was pinned. One is at maximum excitation and at minimum excitation. So when it was pinned, our engine RPM was about approaching the maximum, about once again 45,000 RPM, and we had a power output of 191 watts, a voltage output of about 4 volts, and a current output of about 29 amps. When it was at max excitation, our power output was at 1.23 kilowatts, which is the goal when you're running this experiment. When you're running at max excitation, you want to try to get it to 1.23 kilowatts and keep it there at steady state for as long as possible. I think we managed to keep it there for about 5 seconds or 6 seconds. And when the current was at a minimum, it was about 0.009 amps or 9 milliamps. And we had a power output of assumingly 0. The actual number came out to be about 0.0000137 watts. So essentially 0 power output, which makes sense because our current output and our voltage output were essentially 0 as well. And that's it. Any questions? All right.